Hello everyone. In this lecture, I shall discuss the Legendre differential equation. The Legendre differential equation takes this form: 1 minus x square y double dash minus 2xy dash plus n into n plus 1 y is equal to 0. Here this n is a non-negative integer. Okay, a non-negative integer. So now you see the coefficient of y double dash is 1 minus x square. So 1 minus x square is equal to 0 implies x is equal to plus and minus 1. So except this x is equal to plus and minus 1, all points are ordinary point. Let me mark it equation number 1. Ordinary point of here equation 1. Right. So if all points are ordinary point except x is equal to plus minus 1, preference should be given to x is equal to 0. So x is equal to 0 be an ordinary point. Once x is equal to 0 is an ordinary point. So what will be the power series solution? So we let y is equal to summation n is equal to 0 to infinity an x minus 0 to the power n means x to the power n. Okay, so this means it is a0 plus a1x plus a2x square plus a3x cube plus so on. Okay, so this is the power series solution. So let this y is equal to this be the power series solution. Power series solution of here 1. So this implies we find y dash. So this implies your y dash will be summation of n a, the derivative of x to the power n x to the power n minus 1. You see, if we put n is equal to 0, then 0 into something is 0. So we write n is equal to 1. Okay, if we write n is equal to 0, no harm also, right? If instead if we write n is equal to 0 also, this is okay then. But we write n is equal to 1 because for n is equal to 0, this will lead you to 0. Right, that's why we choose n is equal to 1 to infinity. And if you simplify it, or if you put n is equal to 1, 2, 3, 4, it's same thing as direct differentiation, is a1 plus 2a2x plus 3a3x square plus so on. Similarly, what will be your y double dash? Y double dash is equal to your summation of, you differentiate it x to the power n minus 1, n minus 1 x to the power n minus 2, so n minus 1, n is already there, it is x to the power n minus 2, and you see here, putting n is equal to 0, this will 0, putting n is equal to 1, this will 0, so n is equal to 2 to infinity. However, if I write n is equal to 0, then also no issue. So that will be, or if I open n is equal to 2, then it will be 2a2, or it is same thing as the direct differentiation, plus the derivative of this is 6a3x plus so on. Now we substitute all this thing in equation number 1. Okay, we substitute all this thing in equation number 1. Substituting y dash, y double dash in equation 1, we and simplifying we get a n plus 2 will be, one more thing you see, already one n is there. Okay, so to avoid the confusion, already one n is there, to avoid the confusion we just replace n by m. We replaced n by m. Okay, we replaced n by m. So here n is replaced by here m. Okay, we replaced n by m because already one n is there. So now accordingly we substitute all this thing and it will give me a n plus 2 will be is equal to n minus m into n plus m plus 1 divided by m plus 1 into here m plus 2 am. So here am is greater than is equal to here 0. Putting n is equal to 0, 1, 2, 3, m starts from 0 here because you see am here, we need a0, a1, a2. If we put m is equal to 0, we have a2, right? Since it is a second order differential equation, two constants are there, so there will be a0 and a1, rest will be the multiple of them. So it is minus of putting n is equal to 0, it will m is equal to 0, it will n into n plus 1, n into n plus 1 divided by, in the denominator it is factorial 2 means factorial 2 into a0. So a2 is expressed in terms of a0. Then putting m is equal to 1 here a putting this is m plus 2, this is m plus 2. So a3 will be here minus of n minus 1 into n plus 2 by factorial 3 a1. Likewise here a4 will be for n is equal to here 2, it is a4. You see, putting m is equal to 2, then it will be here a4 is equal to a4 will be this much, and this is here a0. Now you substitute the value of a0 here. Okay, a0 here, we will get it, and similarly we get the other coefficient, and you substitute all this thing here, because equation 2 is my this, let it be my equation 2. So this equation 2 is my solution of 1. Okay, with the power series solution of 1. So now substituting all this thing in equation number 2. Okay, we get this a0 term separated, a1 term separated. So now let I say this is my y1, this a0 into y1, and this I say a2. Now this is a y1 is a function of x, y2 is also a function of x, so y is also a function of x. So now this is the solution. Okay, now you see, as n is a non-negative integer, okay, as n is a non-negative integer means here 0 1 2 3 4 5, you see now, so on. So you see now, if I put n is equal to 0, then what will happen? If I put n is equal to 0, so this will 0, this will 0, okay, this will 0, right? So in y1 only 1 will be there. Now if I put n is equal to 2, you see, if I put n is equal to 2, then this is n minus 2 is there, so this will 0. So henceforth this will 0. So there will be only 2 terms. Okay, so means y1 will terminate, y1 will have the finite number of terms, means y1 is a polynomial. Similarly, if I put n is equal to 1, you see, then this is 0, this is 0, means it is only x. Similarly, if I put n is equal to 3, then this onwards is 0, so we are getting only 2 terms. So for n is even, y1 is a polynomial. Thus for n is even, y1 is a polynomial, and y2 is an infinite series, and for n is equal to odd, okay, y1 is an infinite series, but y2 is a polynomial. So what we conclude? This partly it is a polynomial, this is a polynomial. So we conclude that the Legendre differential equation has a polynomial solution. Okay, so we conclude that, and in fact we see here y1 is equal to 1 when here n is equal to 0. Okay, and y0 is equal to 1, n is equal to 0. Sorry, for n is equal to 0, here y1, this is my y1 is equal to 1. For n is equal to 1, 2, we have putting first 2 terms, this and this, it will be here y1 is equal to 1 minus 3x square. And similarly for n is equal to 4, here y1 will be 1 minus 10x square plus 35 by 3 x fourth. Okay, similarly for n is equal to here 1, here y2 will be x, n is equal to here 3, here y2 will be here x minus 5 by 3 x cube. Okay, so we are getting like this. In general, what we conclude? Legendre differential equation has a polynomial solution. Legendre differential equation has a polynomial solution. And in fact, so we conclude, so therefore we replace here y, right? This yx is replaced by here pnx, since it is a polynomial. So therefore we write, so this y is replaced by here pnx. Okay, so what we conclude? So therefore your Pnx is equal to a0 y1x plus a1 y1x. Now however, this Pnx is said to be Legendre polynomial. Okay, Pnx is a Legendre polynomial if it satisfies the condition. If it satisfies the condition, Pn1 is equal to 1. Pn1 is equal to 1. This condition is important. This condition is important. Under this condition, we can get the value of a0 and a1. And if you simplify it, we have p0x is equal to here 1. P1 is equal to x. P2 is equal to 1 by 2 3x square minus 1. P3 is equal to 1 by 3 5x cube minus 3x. And P4 is equal to 1 by 8 35x fourth minus 30x square plus 3. Okay, because we impose this condition Pn1 is equal to 1, and with this value and we get this coefficients. Accordingly, these are the first 5 Legendre polynomials. These are the first five Legendre polynomial. However, to get this Legendre polynomial, we have a general formula. So now to get all these things, we have a general formula. Okay, the general formula for Pn. So this Pn is given like this. Summation r is equal to 0 to capital N 2n minus 2r factorial. Now what is into x to the power n minus 2r divided by this. So what is this capital N now? So now this capital N is nothing but a small n divided by 2 greatest integer function. Greatest integer means you must be knowing, if I say 2.7, so it is here 2. Okay, the whole part, not the fractional part. Minus 3.5, it will be here minus 4. 0.9, it will be a 0, in that way. So this must be here n by 2 if n is equal to here even, and n minus 1 by 2 if n is equal to here odd. Accordingly, we can solve to get the Legendre polynomials. In fact, if we put suppose here n is equal to 0, then what will be your capital N? Capital N is 0 by 2 greatest integer is here 0. So what will happen to your Pn0? Your Pn0 will be summation of r is equal to 0 to 0, means only one term. It is n is equal to your 0. So you see, for Pn is equal to 0. So n is equal to 0. Your Pn0 means we are r0 and n0, means we have r0 and n0, isn't it? So you put r0 and n0 this, so it will give you 0 factorial x to the power 0 divided by 2 to the power 0 factorial. So this is your 1. So what we are getting p0 is equal to 1. Again, if we put here, suppose n is equal to here 1, then here n by 2 is here 0 by 2 greatest integer, 0.5 greatest integer is here 0. So here Pn 1 will be P1, sorry. So this will be P00. You see, the first term will be P0x. Okay. So what we conclude here, P0x, or short I write P0 is equal to 1. Now for n is equal to here 1, we are getting what? We are getting P1x. Okay, P1x. So it will be summation of r is equal to 0 to 0. But here you see n is equal to 1 and r is equal to 0. You substitute here n is equal to 1 and r is equal to 0. You substitute here only one term. So it will give you only x. So therefore P1x, or simply P1, is equal to x. If I substitute now here n is equal to 2, if I substitute here n is equal to 2, then n by 2 is here 2 by 2 greatest integer is here 1. So here summation varies from r is equal to 0 to 1. So this thing. So here you see, here n is equal to 1 here, but r varies from r is equal to 0 and r is equal to 1. You have two terms. So if you split it, this will give you two terms. Okay. So after simplification, this will give you 1 by 2 3x square minus 1. Okay. So therefore your p2x is 1 by 2 3x square minus 1. This is your third legendary polynomial. In that way we can continue. Also we have one more thing, the Rodrigues formula for the legendary polynomial. Another important formula is the Rodrigues formula for legendary polynomial. It is Pnx is equal to 1 by 2 to the power n factorial n nth derivative of dn by dxn x square minus 1 to the power n. Okay. Also this formula will lead you to the legendary polynomials. If you have your n is equal to 0, this will give you p0x will be 1 by 2 to the power 0 into 0 factorial d0 by dx0. It is x square minus 1 to the power 0, means it is here 1 only. So it is here 1 only. If I put n is equal to 1, then here p1x is 1 by 2 to the power 1 into factorial 1, first derivative of x square minus 1. So this will be 1 by 2 and the derivative of x square is 2x. So it is equal to your x. Okay. So therefore your p1 is equal to x. Accordingly, if I put n is equal to 2, right, I can put 1 by 2 p2 is 1 by 2 3x square minus 1. If I put n is equal to 3, I can find p3 is equal to 1 by 2 5x cube minus 3x. Okay. Accordingly, I can generate all the legendary polynomials. Now coming to the generating function for legendary polynomial. The generating function is summation n is equal to 0 to infinity pnx u to the power n is 1 by 1 minus 2x u plus u square root over, or I can write it 1 minus 2x u plus u square to the power minus half. Okay. So this is the generating function for the legendary polynomial. If I ask what is pnx, this pnx is nothing but, what is this pnx? Pnx is coefficient of u to the power n in the expansion of this, if we expand it, okay, in the expansion of this, in the expansion of this, is not it? If we expand it, binomial expansion, and you collect the coefficient of u to the power n, coefficient in the expansion of 1 minus 2xu plus u square to the power minus half. If you apply the binomial expansion and you collect the coefficient of u to the power n, and it must be here pnx. So this is the generating function for the legendary polynomial. On this basis, we can have several properties. If I ask you the orthogonal property, that you have export mana that is what I think. The orthogonal property is like this: integral minus 1 to 1 pmx into pnx dx, okay, is equal to 0 if m is not equal to n, is 2 divided by 2n plus 1 if m is equal to n. Okay. Suppose you are asked integral minus 1 to 1 p2 into p3 dx, obviously it is 0. If you are asked to verify, then you have integral minus 1 to 1 p2 is 1 by 2 3x square minus 1 and p3 is 1 by 2 5x cube minus 3x. Okay. If you multiply it, we find odd power of x. This is a odd function, minus 1 to 1 odd function. So this integral is 0. If I ask you integral minus 1 to 1 p3x into p3x dx, then it must be, the value of p3 is this, it must be a 2 by 2 into 3 plus 1. So this is equal to 2 by 7. This will be your answer. In fact, if you are asked to verify minus 1 to 1, P0 into P1x. Okay, so it must be 0. Minus 1 to 1. Okay, minus 1 to 1, P0 is 1 and P1 is your x dx. So this is odd function. Odd function means 0. If you integrate it, x square by 2 minus 1 to 1. Okay, so here 1 by 2 minus 1 by 2 is here 0. Similarly, if I ask minus 1 to 1, P1 square dx. So it must be minus 1 to 1 x square dx. Okay, so this is 2 into 0 to 1 x square dx. So this is equal to 2 into here x cube by 3. So this is 0 to 1. So this is 2 by 3. And what is by the formula? It is 2 by 2n plus 1. 2 into 1 plus 1. Is it not here 2 by 3? Okay, so this formula is valid here. So this is because of the orthogonal properties, right? Now coming to some more properties. Suppose you are asked prove Pn1 is equal to 1. This is one property, right? If you want to prove here the generating function for Legendre polynomial is Pnx u to the power n summation n is equal to 0 to infinity is 1 minus 2xu plus u square to the power minus half. If I put Pn1, we need x is equal to 1. Then what I am getting? This is summation of Pn1 into u to the power n. So in the right hand side it is 1 minus 2u plus u square to the power minus half. So this is 1 minus u whole square to the power minus half. So this is 1 minus u whole square to the power minus half. So this is 1 minus u whole square to the power minus half. So this is 1 minus u whole to the power minus 1. Okay, so this is here 1 by 1 minus u. You must be knowing the binomial expansion. It is 1 plus u square plus u cube means it is summation of u to the power n. So now what is the coefficient of u to the power n here? This is 1. The coefficient of u to the power n is 1. So comparing the coefficient of u to the power n, we get Pn1 is equal to here 1. Likewise, come to the second property, Pn minus 1 is minus 1 to the power n. Right? Property number 2 say Pn minus 1 is minus 1 to the power n. If likewise you can prove it, the generating function is Pnx u to the power n is 1 minus 2xu plus u square to the power minus half. If you put your x is equal to minus 1, so this will be summation Pn minus 1 u to the power n. This will be 1 plus u to the power minus 1. So this is 1 by 1 plus u binomial expansion. Alternatively, it is 1 minus u plus u square minus u cube. Okay, it will move like this. So the general form here is minus 1 to the power n into u to the power n. Now if you collect the coefficient of u to the power n, right? Coefficient of u to the power n, then what you will getting? Comparing coefficient of u to the power n, we get Pn minus 1 is minus 1 to the power n. Okay, so similarly some other properties. Now coming to this property, Pn dash 1 is this. We have the Legendre differential equation. 1 minus x square y double dash minus 2xy dash plus n into n plus 1 y is equal to 0. Since this Legendre differential equation has a polynomial solution, okay, so replace y by pnx. Okay, so what we are getting, that is what I am getting, 1 minus x square pn double dash x. Okay, then minus 2x, it is Pn dash x, plus here n into n plus 1 into Pnx is equal to 0. Right? Means just we replace y by Pnx since Legendre differential equation has a polynomial solution. Now here if I put here x is equal to 1, put x is equal to 1, what I am getting? This is 0. 0 minus 2 Pn dash x, and it will be plus n into n plus 1 Pn1, right, is equal to 0. But Pn1 is 1. You know what is Pn1? Pn1 is here 1, already we have proved it. So that means here 2 Pn dash x is equal to Pn dash 1. It becomes here 1 because we have taken x is equal to 1. So it will be here n into n plus 1. N into n plus 1. So that means what is here Pn dash 1? It is n into n plus 1 by 2. Coming to another property number 4. Property 4. It is Pn dash minus x is minus 1 to the power. So this property is Pn dash minus 1. And previously we have proved Pn dash 1. So now Pn dash minus 1. Now the same way here we put, okay, put x is equal to minus 1. What we are getting? This is 0. Minus it is here plus 2 Pn dash minus 1 plus n into n plus 1 Pn minus 1 is equal to 0. What is Pn minus 1? It is here minus 1 to the power n, is not it? So this implies here 2 Pn dash minus 1 is minus of n into n plus 1. Minus 1 to the power n, I may write it minus 1 to the power n minus 1, n into n plus 1, right? Then what is here Pn dash minus 1? It is minus 1 to the power n minus 1, n into n plus 1 divided by 2. If I write minus 1 to the power n minus 1 or minus 1 to the power n plus 1, no harm, okay? No harm. If one want to write it minus 1 to the power n plus 1, n into n plus 1 by 2, that's also fine, then no issue. We can also, one may also write it minus 1 to the power n plus 1, n into n plus 1 by 2, no issue, okay? We may write this or this. Now coming to few more properties. Now proving property number 5. Pn minus x is this. So we have the generating function. The generating function for Legendre polynomial, it is summation of Pnx u to the power n is 1 minus 2xu plus u square to the power minus half. If I replace x by minus x, okay, so putting x by minus x, we have here x Pn minus x into u to the power n is here 1 plus 2xu plus u square to the power minus half. I can write it 1 minus 2x into minus u plus minus u whole square, is not it? This to the power minus half. Now you see this to the power here minus half. Now you see, now this is same thing as this. Now this is the Legendre generating function. If you compare these two, wherever there is u, here is minus u. So this will be, take this form here, Pnx minus u to the power n, is not it? So now I can write it Pnx u to the power n into minus 1 to the power n, is not it? So now what is the coefficient of u to the power n? If I collect the coefficient of u to the power n, so this is the coefficient of u to the power n and this is the coefficient of u to the power n. Comparing the coefficient of u to the power n, we get Pn minus x is minus 1 to the power n Pnx. So this is proved, okay? Coming to property number 6. So coming to the proof of this, we have the generating function for Legendre polynomial is summation of Pnx u to the power n is 1 minus 2xu plus u square to the power minus half. So you see, what is Pnx? As I have told you, Pnx is the coefficient of u to the power n in the expansion of this, is not it? So similarly, u to the power p2n, if I put p2n 0, then what will happen here? It should be the coefficient of u to the power 2n in this, with here x is equal to 0, with 1 minus 2 into 0 into u plus u square to the power minus half, is not it? Because x is 0 here, so this is coefficient of u to the power 2n in 1 plus u square to the power minus half. You may recall here 1 plus x to the power minus n. Okay, it will be 1 minus nx plus n into n plus 1 by factorial 2x square, and it will go like this: n plus 1, n plus 2, n plus r minus 1 by factorial r x to the power r, in that way. So this is my general term. Okay, this is my, it will go plus and minus, it is minus 1 to the power r, right? It is, if it is minus, then all are plus. Since it is plus, so this is alternatively minus and plus. So this is the formula. So with this formula, so now this coefficient will be how much? This coefficient will be here minus 1 to the power n. It is half plus 1 and half plus 2. If you go on continue, it is half plus n minus 1 divided by factorial n. Okay, so if you simplify it, it will give you minus 1 to the power n 1 3 5 2n minus 1 divided by 2 to the power n into factorial n. If we want to further simplify, you have a gap here 2, you have a gap here 4, you have a gap here 2n. If I multiply this thing in the numerator, then the numerator becomes here minus 1 to the power n factorial 2n. And to fill this gap, what we multiplied, it is 2, 4, 6 up to 2n we have multiplied to get this form. So now taking 2, 2, 2, right, n times, it is minus 1 to the power n 2n factorial, it is 2 to the power n factorial. Again taking 2, 2, 2 n times, it becomes here 1, 2, 3 up to here n. So this is equal to here minus 1 to the power n 2n factorial, it is 2 to the power 2n. Okay, 2 to the power 2n, it is factorial n, it is factorial n into factorial n whole square. So it is proved. Okay, it is proved here. It is proved here. Now you see, there is no odd power of u here. Okay, there is no odd power of u, see. So here, since I am taking u square here, it is u square to the power 1, u square to the power 2. So there is no odd power. So coming to proof B, since there is no odd power of u to the power n in the expansion of 1 plus u square to the power minus half. So therefore p2n plus 1 0 is equal to 0. There is no odd power. Already you have proved 7 properties, and I can say that it is 8, 9 and 10. This property number 8 is called the Bonnet's recursion. And from this Bonnet's recursion we can prove this. How this Bonnet's recursion can be proved? We have the generating function for Legendre polynomial. Pnx u to the power n is 1 minus 2xu plus u square to the power minus half. Now you differentiate with respect to u. And proceed. And this thing will be generated from this Bonnet's recursion. Okay, these are the assignment for you. You should solve it. Clear? So now to conclude, the summary is like this. We have a Legendre differential equation. You should remember it. And here n is a non-negative integer. Now put for n is even, here one part is polynomial, other part is series. Similarly for n is odd, one part is polynomial, other part is series. That's why we conclude that the Legendre polynomial has a Legendre differential equation has a polynomial solution, and that polynomial solution Pnx is said to be a Legendre polynomial. It satisfies the condition Pn1 is equal to 1. From this condition, okay, you can generate the Legendre polynomial. P0 is your 1, P1 is your x, P2 is your 1 by 2, 3x square minus 1. You should recall this. And P3 is equal to 1 by 2, 5x cube minus 3x. Likewise, here P4 is equal to 1 by 8, 35x fourth minus 30x square plus 3. All this case you see, this condition must be there. Pn1 is equal to 1. So from the Rodriguez formula, you can generate this also. Okay. Then furthermore, you should have the 10 properties. 7 I have already proved. These 3 I have asked you in terms of the assignment. Okay. So at this stage, the video is getting lengthy. I should conclude here. If you feel this lecture is useful and interesting, please like and subscribe to this channel, which will boost my motivation and which will help to upload the subsequent lectures for your benefit. So thank you all. Have a nice day.